We're recording the meeting. So let me introduce our speaker for today. He is Dr. Shawn Xiang from UC at Irvine. Shawn had earned his PhD degree in biomedical optics from South China Normal University, and his postdoctoral training was done in medical physics at the Stanford Medical School. He joined the UC Irvine in 2020 as a tenured associate professor with joint appointments in the Department of Radiological Sciences and the Department of Biomedical Engineering. He is passionate about developing innovative ultrasound imaging modalities and translating them into clinical practice. His research has led to more than 70 peer-reviewed journal papers and 30 conference papers, and submitting 14 patents, 7 of which have been awarded. He has received numerous prestigious awards, including the NIH Merit Award, the R37, University of California Irvine Outstanding Mid-Career Faculty Research Award, the American Cancer Society Cancer Research Scholar Award, and Best in Physics Award from the American Association of Physicists in Medicine. Shawn has been a key contributor to the invention of X-ray induced acoustic computed tomography, what's known as XACT, and electroacoustic tomography, EAT, for electroporation monitoring. And today he's planning on discussing 3 projects related to radioacoustic imaging in his presentation. The first of which is in vivo dosimetry and image-guided precision radiotherapy. The second is precision nano knife. And the third is portable and ultra-fast CT. So Shawn, the floor is yours. Please go right ahead.
Thank you so much, Dr. Tata, for the kind introduction. And thank everybody for taking your time to joining us today. And especially thank NCI for inviting me to speak at this webinar. It's my great honor, and I'm very excited to report some of our recent progress on radiation-induced acoustic imaging and the possible application in therapy monitoring and diagnosis as well. Again, my name is Shawn, and I'm from UC Irvine. Really, I'm going to focus on my talk on 3 different projects. The first one is radiation-induced acoustic imaging and how it can contribute to in vivo dosimetry for precision radiotherapy. And then the second project is more of like image-guided precision nanolife. And lastly, I will talk about the new alternative to CT. It's a portable, very, very fast CT imaging. We call it X-ray CT imaging. So imagine that you're a cancer patient, and then you're lying on the couch, you're about to receive radiation therapy. So you kind of trust you will receive the exact radiation dose that can just treat your tumor. So what if I told you, I'm sorry, we're not 100% sure if indeed you will receive that amount of radiation dose needed, because we don't really have a way to directly measure radiation dose that's been delivered to the tumor. And even there's no way to visualize radiation beam in the patient. In the case of you have tumor motion involved, we're not sure if that radiation beam indeed is hitting the targets. We do have a lot of computer simulation, Monte Carlo simulation to do treatment planning, and we have dose verification in the water tank. We can measure the dose on the surface of the patient, but we don't have any way to measure the dose for just to verify the dose delivered to the tumor on the patient. So that's actually what our research is aiming to change. So keep that in mind. I start my personal research journey back in 2012 when I was a postdoc at Stanford, work with Dr. Xiang in the radiation oncology department. And then we were asking either any way can visualize radiation beam and also quantify the dose right on the tumor in the patient. So that's how we kind of invented this XACT imaging. Basically, what we found is whenever you're treating the tumor with those X-ray photon, and you're going to produce some type of ultrasound, and that ultrasound strength is proportional to how much dose is being deposited to the tumor. And we have the first ever XST imaging on that paper. But so what is radiation-induced acoustics? So basically, we believe as if you have any type of radiations, not just X-ray, proton, anything, laser, and electric beam, they're gonna produce ultrasound wave, and with the ultrasound transducer, we can pick up those ultrasound and we can do imaging. So the concept is just like a relay game. You have radiation goes in, and you have ultrasound comes out. So how exactly it works? I often have this analogy, which is lightning sounder. So in this case, you have a lightning bomb. It is electromagnetic energy. It is interact with air in the atmosphere. That air will be quickly heated up and expand. So you would have this sonic bomb, which is a thunder. So now all you have to do is start listening. Let's say if you count for 3 seconds, you multiply it by the speed of sound in the air, roughly 340 meters per second. You get about 1 kilometers. Now you know the sounder, the lightning is happened around 1 kilometer away from you. And also based on the amount of sound you heard, you can estimate how strong the lightning event is. So the point is very simple. Based on the sounder you heard, you can estimate both the location and the strength of the lightning events. So we use exactly the same concept for these biometric applications. Instead of lightning, we have this short pulsed radiation. And that happens to be true in radiation therapy. You have microseconds, even shorter radiation pulse. And then it delivered energy in a human body, and there will be some very tiny temperature rise, typically in the millikelvin. And then it's going to produce ultrasound. That ultrasound is strong enough for us to detect for imaging. So how do we do imaging? Imagine that you have a pointer source, and then you have one detector. So you know the lightning is happening on this circle, but you don't know exactly the location. However, if you have 3 such measurements, you can easily pinpoint the location of these lightning events. And we have more than 3 detectors. We have hundreds of those detectors in the ultrasound array. We can easily figure out what's the dose distribution within the human body with those equations. And we have got that imaging, and you see the radiation beam, but to get a quantitative dose information is a different story. You can see the shape of the beam, but quantify the dose is pretty challenging. So we have worked very hard by developing new imaging reconstruction algorithms like model-based reconstruction and time reversal reconstruction, and also deep learning as well. Eventually, we get a color-coded dose map. If you look at the dose map here, different color give you different dose. So now we're not only visualize the beam, we know the shape of the beam, but also we produce a color-coded those information to the physician. They know exactly which location has exactly how much dose being deposited there. We're one of the major group doing this, but also we have a lot of competitors, and one of the group in Michigan from Isam used to be in Michigan, and then he moved to Florida, and then Shirin is in Michigan. They have this wonderful work on NINAC using the radiation acoustic imaging. They did the first patient study just last year, and you have this beautiful C-shaped treatment plan with radiation acoustics, and you can easily overlay those images with planning CT. So that, I think that's the milestone of this technology. It's actually the technology itself is evolved very quickly. So think about, we have this idea from a lab about 10 years ago, and it quickly evolves, and we have the first patient study just last year. So the similar idea can be expanded to proton therapy as well. As we know, proton therapy takes the advantages of using this so-called black peak, and you can imagine that if we have the black peak is right on the tumor, we can minimize the radiation to the skin of the patient. But the question is, how do you know where the black peak is, right? We need a way to measure the black peak, to localize the black peak. And also, I want to point it out, proton therapy used to be very expensive, bulky, and not many proton facility across the country, even over the world. But now it's kind of exponentially grow. We have more than 100 operational proton center right now, and we have more to construct. I think it's very exciting if we can have an imaging modality that can localize the black peak. That'd be great. So as I mentioned, there are many facts that contribute to this range uncertainty in proton therapy. You have interfraction changes because of the size of the tumor and location of the tumor might change, but also you have this interfraction motion. So indeed, we need a imaging technology that can localize black peak. In fact, measure the proton-induced acoustic signal was tracking back to 1995 from a Japanese group. They actually detect the first proton-induced ultrasound signal, but at that time they have to average in like 10,000 of those proton beams to get a decent signal. So back in 2015, we kind of regain the interest for the proton acoustics, and also there's other groups in Germany like Katia Paradis group, and in United States from UPenn, Stephen Avery, they also did a lot of measurements. So we start from there, and took us several years to really improve the signal to noise ratio. And one of the work we did is we really built a dedicated amplifier system by working with Dr. Yung Chen's group in Oklahoma. They have a proton center there, and we kind of have another milestone achieved, which is we can detect a single proton pulse. These are just clinical proton machine. We actually can measure each single proton pulse in the clinic with this dedicated amplifier system. And to measure the range of the proton is principle is very simple. You have time of flight information with the peak of the proton acoustic signal, and then as you can see, if you shift energy of the proton, this is how you change the penetration dependence of proton therapy in clinic. And then you can say the proton acoustic signal, the peak also changes. and you multiply by the speed of sound in soft tissue, you roughly know the location. And this is the basic principle how we measure the location of the Bragg peak. We have a lot of studies, and really we have demonstrated that we have about sub-millimeter accuracy in those measurements, even with very few or without averaging for single pulse detection. So instead of doing this point measurement, we actually develop a 3D imaging system with a matrix array. We have 16 by 16 inanimate that give us this 3D proton acoustic imaging system. We just put it right in front of the Bragg peak. We can, I don't have time to go through the system itself, but basically it's kind of a matrix ultrasound array, and then we build a preamplifier system, data acquisition system, and we can use it for 3D imaging. So in the experiment, it's pretty easy to do the experiment. We have proton machine, and we have this we call it human TOSA phantom. It's a phantom has exactly the same structure, anatomic information as human, and but we have different properties of to the X-ray, to the proton, to the ultrasound. Now we have a robotic arm. We can hold the transducer at one location, and then we fix the location. Now, if you change the energy of proton, and we can imagine this Bragg peak in 3D. So I'm going to show you one example. So this is the first 3D Bragg peak imaging with our proton acoustic imaging. And you can see the Bragg peak in different plan, in XY, YZ, XZ plan. And also, we can make this video to track the pencil beam scanning in clinic. So you have the scanning gap as 10 millimeter in distance versus 5 millimeter in distance. We can real-time tracking those scanning. Also, we have explored so we can do everything with the conventional proton machine, but also we're trying to say if our technology can apply to flash therapy as well, because as you guys may know, this flash radiotherapy has much higher dose rate, especially has much higher instantaneous dose rate. Dose rate can go up to like millions of grid per second with this very short pulse, typically like around 1 microseconds. So we have worked with Mavion, is a proton vendor, and we go to their headquarters and we are work with their VP Townsend's group. We have got the measurement for the flash proton therapy. As you can see, we increase the dose rate all the way up to here the graph shows like 50 grid per second, but actually we can measure like 100 grid per second, even more. And the instantaneous dose rate is up to millions grid of per second. And also we got this nice 3D imaging without much of averaging, very high, very strong proton acoustic signal in the experiment. And also we have done actually proton, but also we have done experiment with electron. So because the electron flash has even higher dose in each pulse, by working with Mary and Catherine's group in Switzerland, also recently with Emil's group in MD Anderson, we have measured the dose up to about 5 grid per pulse. And I can quickly show you guys a video here on the right. So the figure A is the flash electron beam in the water. So you don't see much of the fluctuation in the water of the electron beam, but the one on the right is the electron beam in an animal, And you do see a lot of variations in each pulse, but that might be because of the electron beam itself, and also might be the different heterogeneity of the animal itself with different tissue type. But anyway, we can measure a single pulse in a flash therapy. I think that would be a very important tools to verify the dose being delivered to the patient, eventually to accelerate the translation of flash therapy. Just a quickly summarize of the work on radiation acoustic image guided radiation therapy. So we want to build a workflow, and we want to change, if possible, to change the clinical practice. As we know, we always take a planning CT before the treatment, and then in our case, we're gonna have this robotic arm hold ultrasound scanning. We hope we can have a whole body or panoramic ultrasound 3D imaging, and we can co-register this ultrasound with planning CT. So we're not only see this traditional imaging with CT, but also we have some type of soft tissue information. And with that, we kind of know the boundary of the tumor, at least of the organ, and then we fix the transducer there, and we can imagine this radiation acoustic imaging to know where the radiation beam is. And we can quantify how much dose being delivered if we have misalignment of the radiation beam and the tumor itself. We can do adaptive radiotherapy. That's something we really like to do in radiation therapy, but we're not be able to do it because we don't have a in vivo dosimetry. We cannot verify the radiation dose on the patient. But now we have these new tools. We might be able to help basically to build a closed loop in radiation therapy rather than traditionally it's open loop. You have the computer simulation, you verify the dose in a water tank, and then you deliver the dose without verifying them, without adapt the treatment. So that's the work we're doing. It's ongoing project, and we are aiming to have the first patient study maybe later this year. And if it's successful, we're going to expand by working with multiple centers to do hopefully multi-center clinical trials later. So that was for the first project, using radiation acoustic for in vivo dosimetry to improve the precision of radiotherapy. And the second project, I'm going to talk about this precision nanoknife. All this work I mentioned before, we're using X-ray LINAC, we're using a proton machine, treat the tumor, which is great. But let's face it, these are very, very expensive machines. Let's say the cheapest proton machine is $30 million. And I was thinking, is it possible to have a machine that much more cheaper, let's say $100,000, and it can treat the tumor, and also it's portable. The patient doesn't have to go a big medical center, and we don't need CT/MRI to do imaging guidance. So it's like we can put everything in a suitcase, and then we can take it to anywhere in the world, and we can treat the patient. It's just the concept is like Starbucks, drive through, and then you have patient in and out. You finish treatment. That's what this irreversible electroporation comes in. So I can quickly show a video to say what is a IRE if you don't know this treatment before.
Harnesses the power of irreversible electroporation to effectively destroy diseased tissue without the need for thermal energy. minimally invasive needle electrodes are positioned in or around the diseased tissue using real-time ultrasound guidance, or CT. High-voltage pulses are delivered between the electrodes and can be confidently delivered in all segments of an organ to create irreversible nanopores within the cell membrane. This stimulus induces an apoptotic cellular death, resulting in the complete ablation of tissue within the electrode configuration. The body responds to the apoptotic-like cell death by initiating the removal of cellular debris. Delivery of non-thermal energy ensures the conservation of the extracellular matrix. The unique mechanism of action enables the preservation of vital structures inside the ablation zone, facilitating the histological and functional regeneration of tissue following treatment. The nanoknife system reimagines localized therapy.
So, but the takeaway message is this is the non-radiation cancer treatment. It's just like a surgical tools, but without using thermal energy, by using this high voltage electric field, by destroying the cancer cells membrane, eventually kill the cancer cells. So it's been there for a while, and people are using this in the clinic. But the problem is you have reversible range and you have irreversible range. So if you don't have enough coverage with IRE, which is irreversible coverage of the tumor, there would be the recurrency of the tumor. And also, traditionally, they use this commercial device, they using very long pulse duration, say 200 microseconds, and they would have some kind of muscle contraction during the treatment. So we're trying to solve those problems by using the nanoseconds electrical pulse, and also we come up with this new imaging modality. We call it electroacoustic imaging, short as EAT imaging. Basically, whenever you deliver this short nanosecond pulse, you're going to produce ultrasound wave, and with ultrasound transducers, we can do imaging. Similar principle as other protoacoustic, exoacoustic, as I mentioned before. And we have done experiment. We have built the generator, nanoseconds generator. Also, we have the imaging device. We got the first signals, pretty strong signals. And also the sensitivity is very high, even for the voltage down to 60 volts per centimeter, we still can get a signal. So it's very highly sensitive technology. Also, we are trying to compare with our EAT imaging with this TTC staining to make sure our imaging is correlated with those staining, and then we don't have to wait after the treatment to know which areas are IRE, which areas are reversible range. With our imaging, we can tell if we have enough coverage or not to the tumor. And here's some video to quickly show how our technology can be used to tracking the location of the electric field, also the strength of electric field in real time. These imaging speed is up to 100 frames per second. It's very quick. So the first application we were thinking of is for treating the prostate cancer. For people knows about transrectal ultrasound guided high dose brachytherapy in radiation therapy, you would know they use these needles to deliver radiation to treat the prostate cancer. We want to do the same thing, but without using radiation. We have these electric nodes deliver the electric energy, and we have the same transrectal ultrasound. We can guide the needle placement, but also we have this dosimetry information. Hopefully, we can treat it more precisely. And we have built this IRE machine. It's portable. And also we have this transrect ultrasound. We have done experiment on this phantom, prostate phantom. We get a very nice ultrasound imaging. We can correlate it with EAT. And both the treatment device and imaging device are portable. We can put it in a suitcase. We can take it to anywhere in the world. So that's a point. We have some problem in terms of limited view for any type of ultrasound. So we have been working with Dr. Renee's group in Maryland. It's a top AI group for imaging reconstruction. We have, so I would say, mostly solved the problem. As you can see, if without the AI, we have this limited view problem, but with AI, we get a really nice imaging just with those limited view. So we have done animal study with the group at UCI on small animal on mice, and we're about to do large animal study with Tom's group at Duke and also George's group in WashU on these canine models. We want to test if this transrect ultrasound guided IRE treatment, if it's working or not. Can we improve the precision of cancer therapy? So that's our second project. Lastly, I want to quickly mention the if possible, we can use this radiation acoustic imaging for diagnosis purposes. Especially, we want to come up with a tool. It's kind of like alternative to computed tomography, but it's portable and much faster. So before I go into details, I want to quickly take you back to the history of X-ray imaging. So thanks Rankin to discover the X-ray roughly like 130 years ago, and we have this 2D radiography ever since. However, it took us like 70 years, more than 70 years, to go from two-dimensional imaging into 3D CT scan. And then now we know to get a single 3D imaging with X-ray, we have to rotate, we have to get thousands, maybe at least hundreds of projections to get just one 3D imaging. So we were asking a very bold question is, can we get a 3D X-ray imaging just with single projection, not 600 projections? So again, look at the CT, the principle of CT. You rotate the source and detector for many projections, and eventually we put those 2D images into a 3D image. But in X-ray acoustic, you have single X-ray projection. You're going to produce this ultrasound wave, and the ultrasound wave is spherical wave in 3 dimensions. So as long as you have a array of ultrasound, you can get a 3D imaging just with single projection. So if we can do that, firstly, of course, we reduce radiation dose. Instead of have 600 projection, we just have 1 projection. And also we can imaging much faster because we don't do mechanical scanning. And also, I think it's even more important to make the CT machine smaller, portable, because everybody is talking about make MRI portable, make ultrasound portable. How can we make CT portable, right? You think about you have patient in the middle, you have X-ray on one side, you have detector on the other side. Just really challenging to make CT machine portable. But with X-ray CT, we might have a chance to make it portable and small. So we have done this since 2016. We have a lot of computer simulation. We have even did some experiment, but also not just my group. There's other groups like Chu Heng's group in South Korea. They have done experiment. But recently we have some breakthroughs. We have built a system that has a matrix ultrasound array, and we got a 3D imaging just with a single X-ray projection. We have this no-go experiment. You only need a one X-ray projection, and we even did this biological sample with a piece of bone. As you can see, we got this 3D X-ray imaging, and it's comparable to those micro-CT images. And we were thinking we might be able to use this technology for interventional radiology, right? Traditionally, for interventional radiology, we have this 2D fluoroscopy. You have X-rays shining from the top, and you have the detector on the other side. You get a 2D imaging in real time. You have this X-ray movie, but it's 2D. So now if we build a XCT scanner, in this case, we put both the X-ray excitation and ultrasound detection on a single side. So it's a portable device, and we can do 3D imaging. And also you can literally integrate ultrasound and X-ray. So you have this soft tissue contrast with real-time ultrasound with the same ultrasound probe, and also you have the XCT imaging, which give you a very high contrast of the needle information. And also we have tested this contrast agent. These are just clinic X-ray contrast agents. We can get a pretty nice imaging, 3D imaging with our XCT experiment. And if you look at this contrast in different plane, you see a very nice, very good contrast with our device. So again, if we do this with interventional radiology, we can monitor both the needle placement, but also we can imagine the dynamic of contrast agent. We haven't published anything yet, but we're doing animal study. We're gonna present more data to show the feasibility on this application. Just a quick summarize of what I just presented. So firstly, I have talked about how radiation acoustic can be applied for in vivo dosimetry. Again, we don't have in vivo dosimetry so far in clinic practice. We can do computer simulation. We can verify the dose in a water tank. We can measure the dose on the surface of the patient. We don't have any measurement for, or even just verification for the dose being delivered to the patient. And radiation acoustic, I believe it's a very promising measurement, a new imaging modality that can give you the in vivo dosimetry, and hopefully, we can integrate with the current clinic practice, and we can do adaptive radiotherapy. Really, we make the radiotherapy as more personalized therapy, which was not able to do before. It's about 10 years we made great progress, but still there's a lot of work to do. In the coming years, we're gonna integrate it with this robotic arm, with ultrasound, with the planning CT, with everything we're doing in the clinic to change the current practice. So the second project I have presented is to another type of cancer therapy without using radiation, which is irreversible electroporation by break the cancer cells, not DNA, but to break the cancer cells membrane, eventually kill the cancers with those electro needles. So we come up with this transfractal ultrasound. We can monitor in the needle placement, and we can have dose verification. Hopefully, we can treat it much more precisely. The point is you have both the therapy and the imaging together with a portable device, and we can take it to anywhere, and that can benefit a large population of cancer patients across the world. Lastly, I have briefly mentioned that this could be a diagnostic tool because we can, in XCT, we can make it portable and it's faster. The imaging speed is going to be at least 100 times faster than CT. We don't need seconds, couple of seconds to get a 3D imaging. We can get a 3D imaging, let's say 10 frames per second, even faster. That only determined by the repetition rate of your X-ray source, and it's portable. Okay, with that, I want to take a moment to thank my lab members and my collaborators, mostly UCI, and we have worked with Oklahoma group, Dr. Yong Chen's group in the last 10 years on proton therapy, Dr. Nate Ren's group in Maryland on AI algorithms, and also recently with MD Anderson group with Mia for flash electron therapy. And also I work with Dr. Jeff Wang from Los Alamos, trying to push the portable XACT concept forward. We have traveled to Europe, work with Mary Catherine's group for electron flash dosimetry. And we're working with UT Austin group. I didn't present any data today, but they have this laser-driven radiation source for X-ray, for electron, which we're gonna have more data coming out. And we have worked with this company in Houston to make all kinds of a device. And yeah, also Maven as well. Also, I want to thank the funding sources, especially from NIH, specifically from NCI. I want to thank NCI for the strong support to our research. We truly appreciate those financial support. And also, I want to thank our friends and colleagues to believed in our ideals, and I hope we have presented enough progress to keep that trust. Lastly, I want to just quickly mention we're open to collaboration, and if any of you guys have any idea that we can work together, feel free to reach out to me. This is my email, also my lab website. And I look forward to work with you guys. With that, I can stop here and I can answer any questions. I went pretty fast. I want to save some time for questions.
Thank you, Shawn. Yes, we do have some questions and they're in the chat box. But before we get to that, let me ask the panelists if they have any questions that they would like to ask firsthand. If not, then we can move over to the chat. Are you able to see the chat box?
I'm trying to find it.
There should be a cartoon bubble in the lower right corner.
Cartoon bubble in the lower right corner. Say.
Daryl, go ahead and just read out the questions if you can.
Yeah, that'd be great. Sorry, I'm not familiar with
The first one is from Freddie. It says, any thoughts on applying the in vivo dosimetry approach to pharmaceutical therapy agents?
I see. That's a great question. Thank you, Kate. I think radiopharmaceutical, it's a little bit different because this external radiation therapy, they do have this pulse radiation. Let's say LINAC deliver around 5 micron seconds X-ray pulse, and proton beam you have also a couple of micron seconds pulse. Remember the principle of radioacoustic is really you have to have some type of pulse stimulation, and then you have you have expansion, contraction. That's how you create this mechanical wave, ultrasonic wave. I'm not sure for radiopharmaceutical, is your radiation source is a pulsed one? If yes, um, that's possible, but if no, probably that doesn't apply. So we can talk more about that. If you can um, send me an email, we can talk more about that. That's a great question.
Yeah, and the second one is from Ella Jones. And she says, I apologize if this is not obvious to everyone, if this is obvious to everyone. I'm not clear on what we're looking at in the image of ultrasound XAC. Can you please elaborate?
XACT, are you talking about this project? If I assume it's this project. So if you look at this experiment or simulation, I would say in XACT imaging, the imaging contrast, what are we imaging? Basically, we're talking about the imaging contrast is the same X-ray absorption. And I would say anything you can imaging with CT, we have the similar contrast. I guess the point here is we can imagine similar information as CT does, but we can do it much faster, less radiation dose, and also we can make it portable and small device compared to CT. That's, I don't know if I answered your question for that.
Okay. The next one is from Michael. Mike, you want to just go ahead and ask the question, or should I read it?
Oh, I think Shawn covered that the radionuclides themselves wouldn't create a pressure wave that would be detectable, at least with this technology currently.
Yeah, that's what I believe. Thank you,
And
Michael.
Vic has a question. Let me collapse this down and see if I could unmute him so he can ask the question.
Yeah, that'd be great.
Vic, can you go ahead and ask?
So you mentioned with regard to the first part of your talk, the dosimetry study, that you're starting some human studies in the near future.
Yeah.
Can you elaborate on those a little bit? What cancers you're studying and what will be the endpoint for those human studies?
Yeah, as I mentioned, we have we're working with the Oklahoma Proton Center. We have done this human TOSA experiment, so we got a really encouraging results. All those results I showed here is from this human TOSA phantom. So we want to do something similar, but with patient. We were started with liver cancer, and we want to say if we can firstly visualize the beam. Secondly, if we can localize the black peak in real time, and eventually, so that's the first step. And then for the clinical trial, we wanna say if we say the beam and there is a misalignment, we could stop the beam, and also we are getting the ultrasound imaging and co-registered with planning CT and everything. Hopefully, with the development of real-time treatment plan, so hopefully we can do adaptive therapy in real time. Let's say we see the beam is misaligned, we're going to change the treatment plan and we're going to retreat it. And at the same time, we have this in vivo dosimetry information. We can compare, do we have enough dose to the tumor? If not, how many beams we can increase? We can deliver more beams. That's kind of the idea we're trying to do. But still, we have to do the first patient study first.
Thank you. I'll send you an email to discuss some more. Thank you.
Okay, thank you.
I have one more in the chat from my colleague Pat Persona. Says, nice presentation, Shawn. How do you specifically and preferentially target the irreversible electroporation to tumor cells?
That's a great question. Although there's some literature shows maybe RE is more sensitive to cancer cells, but I don't have a concrete evidence for that. I would prefer to believe they pretty much treat everything. That's why we come up with this imaging technology, electroacoustic, to visualize the invisible electric field, but also if we can differentiate which area is RE, which area is RE, so we can make sure we have all this RE region covers all the tumor. We make sure there's no recurrency. Again, to your question, I don't believe it's more it's targeted. So that's why we need a imaging for guidance, I guess.
Okay, the last question in the chat box is from Takashi. And he's asking, is there any model to expect toxicity from the irreversible electroporation to normal tissues? Are there any models to expect toxicity?
Oh, okay. That's a great question. I think we are working with Dr. Zhi's group at UCI to do this animal study. But honestly, this treatment has been there for a while. I would say probably 20 years, 30 years. People have used it in clinic already. I guess the problem we're solving is, number one is to make the pulse duration shorter from 200 microseconds to 100 nanoseconds. In that case, we can reduce the thermal effect. Also, we can reduce the muscle contraction. And the second one is, with this nanoseconds pulse, we have this new imaging modality that we can visualize the electric field, also quantify the dose. That's something nobody have done this before. Honestly, we haven't done any much of toxicity study. I know there's a couple groups they have done this already. I can share some literatures with you if you like to read it. Thank you.
Okay, thank you, Shawn. The last question from me is, I'm curious about the ultrasound detectors that you have. What frequencies do they start with? And obviously, these are broadband detectors, right? I'm curious if you could give some numbers as to what the ultrasound window is that you're looking at.
Right. So, sorry, which device are you asking?
Oh, let's take the first example.
Yeah. Okay. Firstly, this radiation acoustic ultrasound is broadband. It's different than the pulse echo ultrasound, right? You have send out 3 megahertz to get a roughly 3 megahertz back. Radiation acoustic is different. You have this short pulse generate very broadband all the way from, let's say, if we take product acoustic as an example, you have the majority of frequency in the several hundred hertz up to maybe 1 or 2 megahertz. But if you use like electroporation, we have 100 nanoseconds, which is a shorter pulse duration. We can detect ultrasound up to, for example, this transrect ultrasound. I remember it's 5 to 12 megahertz, so it's much higher frequency. XACT, we have 50 nanoseconds. We also have a very high frequency. Again, it's broadband, but there's a center frequency. The universal principle is if you use a shorter pulse duration, you have a smaller targets in your imaging, you're going to generate higher frequencies. If you have a longer pulse duration, bigger targets, you're going to have lower frequency components. But again, it's a broadband. Thank you.
Thank you. Yeah. So we'd like to end here, and I'd like to thank you, Shawn, for the wonderful talk that you've given. And to the members that have joined in, please join us come next month. We meet on every Monday of the every first Monday of the month at 1 o'clock Eastern time. And the link to joining in to finding out which talks are coming up is the one which has been provided for you in the chat box by Dr. SP. So
Thank
we'll
you.
see you.
Yeah.
We'll see you next month. Thank you, Shawn.
Thank you. Bye-bye.
Bye.
Bye-bye.